It is generally not safe or legal to use a commercial snap switch to control a motor. Manual motor starter switches are specifically designed for motor control and provide protection against overloads and other faults. Snap switches are not rated for motor loads and may not provide adequate protection or reliability. Commercial snap switches do not typically have a horsepower rating, as they are not designed for motor control. Manual motor starter switches have built-in thermal overload protection that trips the switch in the event of an overload, preventing motor damage. Snap switches do not provide this protection. Motor starter switches are designed to dissipate heat generated by the motor. Snap switches are not designed for this purpose and may overheat if used with motors. In many jurisdictions, it is required to use a proper motor starter switch for motor control. It is not recommended to use a commercial snap switch to control a 1/2 horsepower fan motor as a temporary solution. This poses safety risks, may violate code requirements, and may damage the motor. It is advisable to wait for the correct manual motor starter switch to arrive. The primary reason for using a manual motor starter switch rather than a standard snap switch lies in the critical overload protection it provides to the motor. Motors, unlike resistive loads such as lights or heaters, draw a significantly higher current during startup, often several times their normal running current. This inrush current, while brief, can stress the motor windings and other components. Furthermore, motors can experience overloads during operation due to various factors such as increased load, mechanical issues, or voltage fluctuations. These overloads, if left unchecked, can lead to overheating, insulation breakdown, and ultimately, motor failure. Manual motor starters are specifically designed to address these challenges. They incorporate thermal overload relays, which are calibrated to trip and disconnect the motor from the power supply when an overload condition is detected. These relays typically use a bimetallic strip or a melting alloy element that responds to the heat generated by the motor current. When the current exceeds a predetermined threshold, the heat causes the bimetallic strip to bend or the alloy to melt, activating a tripping mechanism that opens the motor circuit. The selection of the correct heater element for the thermal overload relay is crucial for proper motor protection. The heater element must be sized to match the full load amperage of the motor. If the heater element is too small, it will trip prematurely, interrupting motor operation unnecessarily. If the heater element is too large, it will not provide adequate overload protection, potentially allowing the motor to overheat and fail. In contrast, commercial snap switches are not designed for motor control and lack the necessary overload protection. These switches are typically rated for resistive loads and may not be able to handle the high inrush current of a motor. Even if the snap switch can handle the initial current surge, it does not provide any protection against sustained overloads. Using a snap switch to control a motor can create several hazards. Firstly, the snap switch may overheat and fail due to the high current demands of the motor. This can create a fire hazard or expose personnel to electrical shock. Secondly, the lack of overload protection can lead to motor damage and premature failure. Replacing a motor can be costly and time-consuming, disrupting operations and increasing maintenance expenses. Thirdly, using a snap switch for motor control may violate electrical codes and regulations. Most jurisdictions require the use of a listed motor starter for motor control, ensuring that the motor is adequately protected against overloads and other faults. Electrical codes like the National Electrical Code, or NEC, provide specific guidelines for motor protection and control. These guidelines are designed to ensure the safety of personnel and equipment. Using an appropriately sized and rated motor starter helps to comply with these codes and avoid potential fines or penalties. Moreover, motor starters often include additional features that enhance motor control and protection. These features may include undervoltage protection, which prevents the motor from restarting automatically after a power outage, phase loss protection, which protects the motor from damage due to imbalanced voltage conditions, and short circuit protection, which provides immediate protection against severe faults. Another crucial aspect to consider is the motor's nameplate information. The nameplate provides essential details about the motor's operating characteristics, including its horsepower rating, voltage, full load amperage, service factor, and insulation class. This information is vital for selecting the correct motor starter, heater element, and other components. Ignoring the motor's nameplate information can lead to misapplication of equipment and potential motor damage. Also, consider the ambient temperature where the motor starter is installed. High ambient temperatures can affect the performance of the thermal overload relay, potentially causing it to trip prematurely or fail to trip when needed. It may be necessary to select a heater element with a different rating to compensate for the effects of ambient temperature. The type of motor also influences the selection of the appropriate motor starter. Different types of motors, such as induction motors, synchronous motors, and direct current motors, have different starting and running characteristics, requiring different types of motor starters. For example, reduced voltage starters are often used for large induction motors to limit the inrush current during startup. In addition to manual motor starters, there are also magnetic motor starters, which use an electromagnetic coil to control the motor circuit. Magnetic motor starters offer several advantages over manual motor starters, including remote control capability, automatic restarting after a power outage, and the ability to integrate with control systems. The specific application and operating requirements determine the choice between a manual and a magnetic motor starter. Remember that electrical work should only be performed by qualified and licensed electricians who are familiar with the relevant codes and regulations. Working with electricity can be dangerous, and improper installation or maintenance can lead to serious injury or death. Always follow safe work practices and use appropriate personal protective equipment when working with electrical systems. In summary, replacing a manual motor starter switch with a commercial snap switch, even temporarily, is not a safe or code-compliant solution. Motor starters provide essential overload protection and other features that are not available in snap switches. Waiting for the correct replacement part is the best course of action to ensure the safety and reliability of the motor and the electrical system. Consider factors such as the motor's nameplate information, ambient temperature, and the type of motor when selecting a motor starter. Always consult with a qualified electrician for any electrical work to ensure compliance with codes and regulations. When dealing with electrical systems and motor controls, there are several critical concepts and calculations that electricians and technicians need to understand thoroughly. Firstly, let's discuss the concept of motor full load amperage, or FLA. The FLA is the amount of current a motor draws when it's operating at its rated horsepower and voltage under full load conditions. This value is typically found in the motor's nameplate and is essential for selecting the appropriate size of conductors, overcurrent protection devices, and motor starters. For example, if a 1/2 horsepower motor is rated at 120 volts and has an FLA of 5 amps, this means that the motor will draw 5 amps when it's running at full load. The NEC provides tables such as Table 430.248 and Table 430.250 that list the FLA values for different types of motors based on their horsepower and voltage ratings. These tables can be used as a reference when the motor's nameplate is not available. Next, let's consider the selection of conductors for motor circuits. The NEC specifies that the conductors supplying a motor must have an ampacity of not less than 125% of the motor's full load amperage. This is to account for the motor's starting current, which can be significantly higher than the running current. For example, if a motor has an FLA of 10 amps, the conductors supplying the motor must have an ampacity of at least 12.5 amps. When selecting conductors, it's also important to consider the ambient temperature and the number of conductors in a raceway or cable. The NEC provides ampacity correction factors and adjustment factors to account for these factors. These factors are applied to the conductor's base ampacity to determine its adjusted ampacity, which must be greater than or equal to 125% of the motor's FLA. Overcurrent protection is another crucial aspect of motor circuit design. The NEC requires that each motor circuit be protected by an overcurrent device, such as a circuit breaker or fuse, to protect the motor and conductors from overloads and short circuits. The size of the overcurrent device depends on the type of motor, the type of overcurrent device, and the motor's starting current characteristics. For example, the NEC allows the use of inverse time circuit breakers for motor circuits which have a time delay that allows the motor to stop without tripping the breaker. The maximum rating of the inverse time circuit breaker is typically 250% of the motor's FLA. For fuses, the maximum rating is typically 175% of the motor's FLA for dual-element time delay fuses and 300% of the motor's FLA for instantaneous trip fuses. The selection of the appropriate overcurrent device is critical for motor protection. If the overcurrent device is too small, it will trip prematurely, interrupting motor operation unnecessarily. If the overcurrent device is too large, it will not provide adequate protection, potentially allowing the motor to overheat and fail. Motor starters are used to control the starting and stopping of motors. They also provide overload protection for the motor. Motor starters come in two main types: manual and magnetic. Manual motor starters are operated manually, while magnetic motor starters are operated electrically using a control circuit. Magnetic motor starters offer several advantages over manual motor starters, including remote control capability, automatic restarting after a power outage, and the ability to integrate with control systems. The selection of the appropriate motor starter depends on the motor's horsepower rating, voltage, and current. The motor starter must be rated to handle the motor's full load amperage and starting current. The motor starter also includes thermal overload relays, which protect the motor from overloads. The thermal overload relays are selected based on the motor's full load amperage and service factor. The service factor is a multiplier that indicates the motor's ability to handle occasional overloads. For example, a motor with a service factor of 1.15 can handle a 15% overload for a short period of time. Control circuits are used to control the operation of magnetic motor starters. Control circuits typically operate at a lower voltage than the motor circuit, such as 120 volts or 24 volts. Control circuits can include push-button switches, relays, and other control devices. The control circuit is used to energize or de-energize the motor starter coil, which in turn closes or opens the motor circuit. Wiring diagrams are essential for understanding and troubleshooting motor control circuits. Wiring diagrams show the connections between the various components in the circuit. There are two main types of wiring diagrams: ladder diagrams and schematic diagrams. Ladder diagrams show the control circuit as a series of rungs on a ladder, with each rung representing a separate circuit. Schematic diagrams show the components in the circuit as symbols, with lines representing the connections between the components. Troubleshooting motor control circuits requires a systematic approach. The first step is to identify the problem. This can be done by observing the motor's operation or by using a multimeter to measure voltages and currents in the circuit. Once the problem has been identified, the next step is to isolate the cause of the problem. This can be done by testing the various components in the circuit to see if they are working properly. For example, if the motor is not starting, the first step is to check the control circuit to see if the motor starter coil is being energized. If the coil is not being energized, the next step is to check the push buttons, switches, and relays in the control circuit to see if they are working properly. Once the cause of the problem has been identified, the next step is to repair or replace the faulty component. After the repair has been made, the circuit should be tested to ensure that it is working properly. Let's delve further into the specifics of motor protection, particularly focusing on overload protection and short circuit protection. Overload protection, as we've discussed, is designed to protect the motor from overheating due to excessive current draw over an extended period. This can be caused by various factors such as a jammed load, a worn bearing, or low voltage. The thermal overload relays in the motor starter are the primary means of providing overload protection. These relays typically use a bimetallic strip or a melting alloy element that responds to the heat generated by the motor current. When the current exceeds a predetermined threshold, the heat causes the bimetallic strip to bend or the alloy to melt, activating a tripping mechanism that opens the motor circuit. The tripping time of the thermal overload relay is inversely proportional to the amount of overload current. This means that the relay will trip faster for higher overload currents and slower for lower overload currents. This inverse time characteristic allows the motor to handle short-term overloads, such as those that occur during startup, without tripping the relay. Short-circuit protection, on the other hand, is designed to protect the motor and conductors from immediate damage due to a short circuit. A short circuit is a fault condition in which current flows through an unintended path, bypassing the normal circuit impedance. This can be caused by insulation failure, a loose connection, or accidental contact with a grounded object. Short circuits can result in extremely high currents, which can quickly overheat and damage the motor and conductors. Overcurrent devices, such as circuit breakers and fuses, are used to provide short circuit protection. These devices are designed to interrupt the flow of current very quickly in the event of a short circuit. Circuit breakers use a magnetic or thermal mechanism to trip and open the circuit, while fuses use a fusible link that melts and breaks the circuit. The interrupting rating of the overcurrent device must be sufficient to handle the maximum fault current that could occur at the installation location. The interrupting rating is the maximum amount of current that the overcurrent device can safely interrupt without being damaged. Selecting the appropriate overcurrent device for short circuit protection involves considering several factors, including the motor's full load amperage, the type of motor, the available fault current, and the interrupting rating of the device. The NEC provides guidelines for selecting overcurrent devices for motor circuits based on these factors. Coordination between the overload protection and short circuit protection is essential for proper motor protection. The overload protection should be sized to protect the motor from overloads, while the short circuit protection should be sized to protect the motor and conductors from short circuits. The two types of protection should be coordinated so that the overload protection trips before the short circuit protection in the event of an overload, and the short circuit protection trips quickly in the event of a short circuit. This coordination can be achieved by selecting overcurrent devices with appropriate time current characteristics. In addition to overload protection and short circuit protection, there are other types of motor protection that may be required in certain applications. These include undervoltage protection, phase loss protection, and ground fault protection. Undervoltage protection prevents the motor from restarting automatically after a power outage. This is important because a sudden restart of multiple motors after a power outage can overload the electrical system. Undervoltage protection is typically provided by an undervoltage relay in the motor starter. Phase loss protection protects the motor from damage due to unbalanced voltage conditions. This can occur if one of the phases of the power supply is lost or if the voltage on one of the phases is significantly lower than the voltage on the other phases. Phase loss protection is typically provided by a phase loss relay in the motor starter. Ground fault protection protects personnel and equipment from ground faults. A ground fault occurs when current flows from a conductor to ground. Ground fault protection is typically provided by a ground fault circuit interrupter, or GFCI, or a ground fault relay. Now let's shift our focus to the practical aspects of replacing a manual motor starter, ensuring a safe and code-compliant installation. Firstly, before commencing any electrical work, it's paramount to energize the circuit completely. This involves turning off the circuit breaker or disconnecting the fuse disconnect switch that supplies power to the motor starter. Use a voltage tester to verify that the circuit is indeed energized before proceeding. Never assume that the circuit is dead simply because the switch is in the off position. Secondly, carefully inspect the existing motor starter and note the wiring connections. Take photographs or create a detailed sketch of the wiring configuration to ensure that you can replicate it accurately when installing the new motor starter. Pay close attention to the wire colors and terminal markings. Thirdly, remove the old motor starter from the enclosure. Disconnect the wires from the terminals, taking care not to damage the wires or the terminals. If the wires are frayed or damaged, trim them back and strip them to expose fresh conductor. Fourthly, install the new motor starter in the enclosure. Mount it securely using screws or other appropriate fasteners. Ensure that the motor starter is properly grounded by connecting a grounding conductor to the grounding terminal. Fifthly, connect the wires to the terminals of the new motor starter following the wiring diagram or the photographs you took earlier. Make sure that the connections are tight and secure. Loose connections can cause overheating and arcing, which can lead to electrical fires. Sixthly, select the appropriate heater element for the thermal overload relay. The heater element must be sized to match the full load amperage of the motor. Consult the motor's nameplate for the full load amperage rating. Use the heater element selection chart to determine the correct heater element size. Seventhly, install the heater element in the thermal overload relay. Make sure that the heater element is properly seated and that the connections are tight and secure. Eighthly, close the enclosure door and secure it with screws or other appropriate fasteners. Ninthly, re-energize the circuit by turning on the circuit breaker or connecting the fuse disconnect switch. Tenthly, test the motor starter to ensure that it is working properly. Start and stop the motor several times to verify that the motor starter is controlling the motor correctly. Use a multimeter to measure the voltage and current in the circuit to ensure that they are within the specified limits. 11thly, label the motor starter with its function and voltage rating. This will help to prevent confusion in the future. Finally, document the installation by recording the date, the name of the installer, and the model number of the motor starter. This information will be helpful for future maintenance and troubleshooting. In addition to these practical steps, it's also important to be aware of the relevant electrical codes and regulations. The NEC provides specific requirements for motor installations, including conductor sizing, overcurrent protection, and grounding. It's essential to comply with these requirements to ensure the safety of personnel and equipment. Also, consider the environmental conditions in which the motor starter is installed. If the motor starter is installed in a damp or corrosive environment, it may be necessary to use a motor starter that is rated for those conditions. For example, a motor starter with a NEMA 4 or NEMA 4X enclosure is suitable for use in wet or corrosive environments. Remember that electrical work can be dangerous, and it's important to take all necessary precautions to protect yourself from electrical shock. Always wear appropriate personal protective equipment, such as insulated gloves and safety glasses. Never work on energized circuits unless you are properly trained and qualified to do so. If you are not comfortable performing electrical work, it's best to hire a qualified electrician. A qualified electrician has the knowledge, skills, and experience to perform electrical work safely and in accordance with the relevant codes and regulations. They can also help you to select the appropriate equipment and materials for your application. By following these guidelines, you can ensure that the motor starter replacement is performed safely and correctly, providing reliable motor control and protection for years to come. And remember, safety first.